Before the world had ever heard of Niels Bohr, the atom was already one of science's greatest mysteries. Scientists knew matter was made of atoms, but what those atoms really looked like inside was still uncertain, like a puzzle missing its central piece. By the end of the 19th century, discoveries were exploding everywhere: electricity, magnetism, X-rays, radioactivity, and all of them pointed to a hidden world beneath ordinary matter. The atom was no longer a simple, indivisible grain. It had a secret structure. Something within it controlled light, energy, and all of chemistry. Yet no one could truly describe what that structure was or how it held itself together. To understand how Bohr changed everything, we must first travel back to the scientific world before him. It was an age of confidence and confusion at once. The mighty framework of classical physics, built by Newton and refined by Maxwell, ruled the universe with elegant equations and certainty. To the physicists of the 1800s, the universe was like a perfect clock, predictable, logical, mechanical. They believed every movement, from the path of a planet to the ripple of a wave, could be explained by simple laws. But the atom refused to obey. When scientists began probing into the heart of matter, they found things that didn't fit. In 1897, J.J. Thomson discovered the electron, a tiny particle carrying a negative charge. This was the first proof that atoms weren't indivisible after all. They had parts, and those parts carried electricity. Thomson imagined the atom like a plum pudding, a sphere of positive charge with little negative electrons stuck inside it like raisins. It was a creative guess, but it didn't explain much. Why didn't the electrons collapse into the center? How did they arrange themselves? Why did elements behave differently? Then came Ernest Rutherford, who in 1911 conducted his now famous gold foil experiment. He bombarded thin sheets of gold with alpha particles, tiny projectiles from radioactive sources, and found that most passed straight through, but a few bounced back as if they had hit something solid. It was as if a bullet had ricocheted off invisible armor. Rutherford concluded that the atom's positive charge was not spread out evenly like pudding, but concentrated in a tiny, dense nucleus at its center. Electrons, he said, must circle around this nucleus like planets orbiting the sun. It was a stunning idea. For the first time, scientists had a vision of the atom that looked like a miniature solar system, a bright nucleus in the center, surrounded by whirling electrons. It was elegant, mechanical, and seemed to fit perfectly with the classical worldview. But almost immediately, cracks began to appear in the logic. If electrons really moved in circular orbits around the nucleus, as planets move around the sun, they should constantly be accelerating. And when charged particles accelerate, they emit electromagnetic radiation. That is, they lose energy. Losing energy means slowing down, and slowing down means spiraling inward. If that were true, every atom in the universe should collapse in a fraction of a second. Yet clearly, the world around us was stable. This paradox haunted scientists. The atomic model that looked so beautiful on paper could not explain why matter even existed for more than an instant. Something fundamental was missing. The physics that worked so well for planets and pendulums broke down at the atomic scale. The universe beneath the microscope seemed to follow rules that mocked human understanding. Meanwhile, experimentalists were uncovering even stranger clues. When gases were heated or excited by electricity, they emitted light, not just any light, but very specific colors, forming bright lines when passed through a prism. Each element had its own fingerprint of spectral lines, its own pattern of light. Hydrogen, the simplest atom, showed a series of lines at precise wavelengths. Scientists could measure these wavelengths with astonishing accuracy, but they couldn't explain why they occurred. Why did atoms emit only certain colors of light and not others? Why not a continuous rainbow? Physicists tried every classical explanation they could imagine. They treated the atom like a vibrating object, like a tiny bell or tuning fork. They imagined electrons oscillating at different frequencies, but none of those ideas matched the observed data. The energy of the emitted light didn't vary smoothly. It jumped between fixed values. This was completely alien to the continuous, predictable world of Newtonian physics. Then, in 1900, a German physicist, named Max Planck, introduced a daring idea while studying blackbody radiation, the glow of heated objects. He found he could explain the data only if he assumed that energy didn't flow smoothly, but came in discrete packets, or quanta. He called the size of these packets h, a constant that would later bear his name. Energy, Planck said, could be emitted or absorbed only in multiples of this constant. At first, even he thought it was just a mathematical trick, not a real property of nature. But that simple assumption cracked open the door to an entirely new world, the quantum world. In 1905, Albert Einstein took Planck's idea seriously and went even further. He used it to explain the photoelectric effect, the way light can knock electrons off metal surfaces. Einstein said that light itself was made of quanta, or photons, each carrying a discrete energy proportional to its frequency. It was a shocking idea. Light, once thought to be a continuous wave, now seemed to behave like a particle. It was neither entirely wave nor particle, but somehow both. The solid ground of classical physics began to tremble. Still, the atomic model refused to make sense. Scientists now had pieces of the puzzle: electrons, nuclei, quantized energy, but no way to fit them together. Rutherford's solar system atom could describe where the particles were, but not why they didn't collapse or how they produced discrete spectral lines. The mathematics of electromagnetism said they couldn't be stable, yet the evidence of solid matter said they were. It was in this atmosphere of confusion and possibility that a young Danish physicist named Niels Bohr entered the scene. Bohr was deeply thoughtful, with a calm yet relentless curiosity. He studied under Rutherford in Manchester, learning about the nucleus firsthand, but he also carried with him an awareness of quantum ideas spreading through Europe. He saw that classical mechanics, powerful as it was, could not capture the mystery of the atom. Something new was needed, a bridge between the old and the new, between the visible world and the invisible quantum realm. Before Bohr, the atom was imagined as a tiny mechanical object. Scientists thought of it as a miniature machine running by the same laws that governed gears, planets, and pendulums. But Bohr began to realize that the atom could not be understood by ordinary logic. It seemed to live in two worlds at once, part classical, part quantum. Its electrons behaved neither like tiny marbles nor like pure waves. They followed strange rules that could not be seen, only inferred through the patterns of light they emitted. The difficulty was not just theoretical, it was philosophical. For centuries, science had been built on the belief that nature could be described in continuous terms: space, time, motion, and force. Quantum ideas shattered that belief. Suddenly, energy came in jumps, not flows. Motion seemed to happen in leaps, not paths, and yet Bohr's generation was standing at the edge of this new frontier, feeling both wonder and fear at what they might find. In laboratories across Europe, experimental evidence piled up faster than theory could explain it. Spectroscopists kept discovering new spectral lines, each more precise than the last. Radioactivity revealed that atoms could transform, releasing tremendous energy. But the mechanism behind it all remained hidden. The old rules were breaking down. It was as if nature had two faces, one calm and predictable for the large world, another wild and discreet for the microscopic one. Scientists began to realize that the atom was not a miniature universe. It was something entirely different, something that operated under a logic beyond human intuition. But without a framework, they were lost. Bohr's genius would be to take all these clues, Planck's quantization, Einstein's photons, Rutherford's nucleus, and combine them into a coherent picture. Yet before he could do that, he had to face the core problem: stability. Why didn't atoms collapse? Why did electrons stay in orbit at all? According to classical physics, an orbiting electron should lose energy continuously as radiation, spiraling inward until it crashes into the nucleus. But that didn't happen. The hydrogen atom, the simplest of all, remained perfectly stable. It could absorb energy and emit light in specific frequencies, but it never disintegrated. Clearly, something prevented the electrons from radiating energy while orbiting in certain states. Bohr sensed that the answer lay in quantization, not just of energy, but of motion itself. He suspected that the atom's stability was not due to a force holding the electrons up, but due to certain allowed conditions, or stationary states, where radiation did not occur. In those states, electrons could orbit indefinitely without losing energy. Only when jumping from one allowed orbit to another would they emit or absorb light. It was a radical idea, one that defied classical logic. Yet it promised to explain both stability and spectra at once. Before Bohr published his theory in 1913, this idea was unthinkable. But all great revolutions begin as heresies. In the early 1900s, physics was standing on the edge of transformation, waiting for someone to unify the scattered fragments into a single vision. The world before Bohr was full of brilliant insights but no harmony. It was a storm of ideas, electrons, photons, nuclei, all swirling in contradiction. The young physicist from Copenhagen would soon bring order to this chaos. But to appreciate the magnitude of his discovery, one must first understand the darkness from which it emerged. The atom, before Bohr, was a mystery wrapped in contradictions. Stable yet impossible, radiant yet unknowable. Science had the data but not the meaning. The old laws of motion and light could no longer explain the smallest scales of reality. The stage was set for a new kind of thinking, one that would demand humility before the unknown. Bohr would later say that anyone who is not shocked by quantum theory has not understood it. That shock began even before his discovery. In this uneasy twilight between the classical and the quantum, the physicists of that era could sense they were nearing something profound, yet the closer they came, the stranger it looked. It was as though nature had hidden her secrets behind a veil of paradox, daring humankind to see through it. And in that tension, between what was known and what could not yet be explained, Bohr found his calling. The world before him was one of elegant failure. Theories that worked for the heavens but not for the atom, equations that described light as both wave and particle, forces that seemed to vanish in the quantum mist. But where others saw contradiction, Bohr saw an opportunity to redefine the foundations of reality. His discovery would not merely describe the atom, it would rewrite the language of physics itself. When Niels Bohr began working on the atomic puzzle in 1912, he was 26, quiet but intense, his mind already shaped by both the clarity of classical reasoning and the bold new whispers of quantum theory. He arrived in Manchester carrying Rutherford's vision of the nucleus in one hand and Planck's mysterious constant in the other. What he needed was a way to reconcile the two. He spent long nights sketching orbits on paper, filling notebooks with equations, crossing them out, starting again. He was not merely chasing a formula, he was trying to hear how nature itself spoke at the smallest scales. He understood that the Rutherford atom could not stand as it was, according to Maxwell's equations. An electron circling a nucleus should radiate energy continuously. That meant every atom should implode. Yet Bohr looked around and saw a world that was stable, enduring, solid. Something had to prevent the radiation from draining energy. He imagined that perhaps electrons were forbidden to exist at arbitrary distances. Maybe nature allowed only certain orbits, as if each electron were confined to specific circular tracks, where it could move without radiating. It was a leap of intuition rather than a product of strict deduction. In Bohr's mind, the atom was not governed by continuous motion, but by quantized states. He began by studying hydrogen, the simplest and purest of all atoms. One electron, one proton, a perfect cosmic duet. Bohr asked himself, if this atom emits light only at specific frequencies, what if each frequency corresponds to a jump between allowed orbits? When the electron falls from a higher orbit to a lower one, it emits a photon whose energy equals the difference between those two energy levels. The spectral lines of hydrogen would then be nothing but the musical notes of these quantum jumps. Suddenly, the mysterious pattern of hydrogen's spectrum began to make sense. Bohr wrote cautiously but with conviction. In his 1913 trilogy of papers titled On the Constitution of Atoms and Molecules, he proposed that electrons move in circular orbits around the nucleus, but only certain orbits are allowed. Each orbit has a specific energy, and radiation occurs only when an electron jumps from one orbit to another. In those stationary orbits, the electron does not emit radiation at all. It is perfectly stable. He even derived mathematical expressions for the allowed energies. using Planck's constant as the key ingredient. The result matched the observed spectral lines of hydrogen with breathtaking accuracy. For the first time, theory and experiment sang the same melody. Those bright lines seen through prisms were not random. They were coded messages from electrons, translating quantum mechanics into color. The Bohr model explained why atoms emitted specific wavelengths and why they were stable. It reconciled Rutherford's nucleus with Planck's quantization. The atom was no longer a collapsing system of charges, it was a structured, quantized harmony. But Bohr's work did more than solve a puzzle. It changed what understanding meant in physics. The orbits he described were not visible or mechanical, they were symbolic representations of allowed states. Classical physics would have demanded to know exactly how the electron moved between orbits, its path, its acceleration, its trajectory. Bohr's theory said, "We cannot know that. The jump is instantaneous, discontinuous. The universe does not slide smoothly from one state to another, it leaps." This was not just a new equation, it was a new philosophy of nature. When Bohr's papers circulated through Europe, reactions were divided. Some physicists were exhilarated, others were skeptical, even offended. The idea that electrons could jump without passing through intermediate positions seemed absurd. To many, it violated every intuition built from centuries of mechanical thinking. Yet the undeniable success of Bohr's predictions silenced many objections. His model explained not only hydrogen's spectral lines, but also the structure of the periodic table and the behavior of chemical elements. It was as if the atom had finally spoken, and Bohr had learned its language. Behind the elegance of the model, however, Bohr knew its fragility. He was aware that his circular orbits were a simplification. He called them symbolic pictures. Useful but incomplete. The real atom, he suspected, would be stranger than any simple diagram could show. But as a starting point, his theory worked wonders. It bridged two eras, the deterministic world of Newton and the probabilistic dawn of quantum theory. The early 1910s were a period of intellectual electricity. Across Europe, the young generation of physicists, Einstein, Bohr, Sommerfeld, de Broglie, Schrödinger, Heisenberg, Pauli, were engaged in a collective awakening. Bohr's work ignited them. It gave form to the idea that energy levels were quantized, that the microcosm had its own rhythm. Arnold Sommerfeld soon extended Bohr's model by allowing elliptical orbits and relativistic corrections, improving its accuracy. The Bohr-Sommerfeld model, as it became known, could predict more spectral lines and even explain the fine structure of hydrogen's light. Yet even then some inconsistencies remained. Electrons still defied full description. Bohr did not mind. He believed that science progressed by confronting paradoxes, not by fleeing from them. To him, contradiction was not a flaw but a compass pointing toward deeper truth. He began to speak of complementarity, the idea that seemingly opposite descriptions, like particle and wave, could both be valid, each revealing a different aspect of the same reality. This way of thinking would later define the entire philosophy of quantum mechanics. In the years that followed, Bohr's atomic model became the foundation of modern chemistry and physics education. Students around the world learned to draw atoms with little circles for orbits and dots for electrons, though Bohr himself knew that such drawings were only metaphors. Still, those images helped millions visualize the invisible. They turned the abstract quantum world into something the human mind could grasp, even if only approximately. The success of Bohr's idea did not mean the end of questions. It meant the beginning of far deeper ones. How exactly did the electron jump between energy levels? Was the jump instantaneous, or did it involve some hidden mechanism? How did the wave-particle duality of light relate to the structure of matter? In the 1920s, these questions would give birth to quantum mechanics proper, with Schrödinger's wave equation and Heisenberg's matrix mechanics. But at the heart of it all remained Bohr's central insight. The atom's energy is quantized, and its stability arises from that quantization. When you look at a simple neon sign glowing red or blue, you are seeing the legacy of Bohr's discovery. Each color corresponds to electrons falling between energy levels in neon atoms, releasing photons with specific energies. Every spark, every glimmer of light emitted by an element is a testimony to the structure Bohr unveiled. Even technologies like lasers, LEDs, and quantum computers trace their ancestry to the moment Bohr dared to say that nature moves in jumps. Bohr's model also changed how scientists saw reality itself. The universe was no longer a smooth continuum but a staircase of discrete levels. Atoms were not mechanical systems but quantum systems, ruled by probabilities and thresholds. This new perspective forced scientists to accept that observation itself affects the observed. Bohr would later argue that there is no sharp line separating the observer from the system. Measurement and reality are intertwined. In the laboratory, human knowledge and nature's behavior are entangled. This was a profound philosophical shift, one that extended far beyond physics. To understand how radical Bohr's vision was, imagine standing in his time. The scientific community was steeped in determinism. Every cause had a calculable effect. Every motion could be predicted. Then came this quiet Dane proposing that the smallest building blocks of matter do not follow continuous laws, that they leap unpredictably between states. It was as if the cosmos itself had poetry hidden in its logic. Bohr's idea offended the mechanistic pride of the era, but resonated with a deeper truth, that nature's essence might be discrete, mysterious, and yet beautifully ordered. Even Einstein, though he admired Bohr, could not fully accept the implications. Their debates became legendary. Einstein argued that the quantum world must have hidden variables, that God does not play dice. Bohr replied calmly that perhaps God not only plays dice but decides the rules of the game. Their exchanges were not fights but philosophical duels, shaping the direction of physics for decades. Through these dialogues, Bohr refined his views, emphasizing that our descriptions of reality are limited by what we can measure. The question, "What is the electron really doing?" may be meaningless unless we define how we observe it. As Bohr's reputation grew, he established the Institute for Theoretical Physics in Copenhagen in 1921, which became the mecca of quantum thought. Young scientists from every corner of the world came to learn and debate under his guidance. The so-called Copenhagen interpretation of quantum mechanics, developed there, reflected his philosophy of complementarity and the role of measurement. But even before that, the roots of his thinking lay in the atomic model of 1913. It was there that the idea first took form, that stability, order, and even existence itself emerged not from continuous laws but from quantized possibilities. Looking back, the discovery seems almost inevitable, but at the time it required immense courage. Bohr had to trust intuition over established logic, to step beyond the boundaries of what could be imagined. He once wrote that every great and deep difficulty bears in itself its own solution. It forces us to change our thinking in order to find it. That was precisely what he did. He changed how the world thought about thinking itself. The world before Bohr was a world of clear outlines, of cause and effect. The world after him was one of probabilities, dualities, and mysteries that could still yield perfect predictions. His model bridged that divide. It gave humanity the first coherent picture of the quantum atom, a stepping stone that would lead to the vast edifice of modern quantum mechanics. Without Bohr's discovery, the later revolutions of Schrödinger, Heisenberg, Dirac, and Feynman might never have found solid ground. The stability of the atom, which once seemed impossible, now appeared natural. The spectral fingerprints of elements, once mysterious, now told their story in precise equations. The very colors of the universe, from the glow of stars to the neon lights of cities, were now understood as expressions of quantized energy transitions. In a single stroke, Bohr had turned confusion into clarity, chaos into order, and yet he never claimed final victory. To Bohr, knowledge was always approximate, always unfolding. He reminded his students that models are not reality, they are ways of talking about reality. Even his own atomic model, successful as it was, would soon be surpassed. But he was never disturbed by that. The goal of science, he said, is not to reveal absolute truth, but to expand the range of what we can explain. As time passed, new theories would refine and replace the Bohr model. Quantum mechanics would describe electrons not as orbiting particles, but as standing waves, clouds of probability surrounding the nucleus. The precise orbits of Bohr's diagrams would dissolve into mathematical symphonies of possibility. Yet, remarkably, the essential spirit of his discovery survived. Every quantum number, every allowed energy state, every emission spectrum still bears the mark of Bohr's original insight, that the atom lives by discrete rules. When we trace the story of atomic theory, we see that Bohr stands at the turning point between two eras. Behind him, the classical age of determinism; ahead, the quantum age of uncertainty. His discovery marked the moment humanity began to glimpse the deep architecture of the universe. Matter was no longer a continuous substance but a pattern of probabilities, vibrating with quantized energy. In simple words, Bohr taught the world that atoms are stable because nature allows only specific places for their electrons to exist. They don't fall into the nucleus because physics forbids it except through precise energy steps. When an atom glows, it's not because electrons slide smoothly downward, but because they leap, releasing light of exact color and energy. That simple idea, almost childlike in its clarity, reshaped science. It explained the glow of stars, the chemistry of life, and the working of every device that uses light or electricity. His discovery was not just about atoms, it was about the human mind's capacity to see beyond common sense. It proved that understanding sometimes requires letting go of what feels logical. The world, Bohr showed, is not obligated to match our intuition. Reality, at its deepest level, dances to rhythms we can sense only through mathematics and imagination. By the time Bohr's model was replaced by the full quantum mechanics of the late 1920s, he had already become one of the guiding lights of science. Yet he remained humble, gentle, and philosophical. Visitors to his institute often found him walking slowly through the halls, lost in thought, pausing to discuss not just physics but language, art, and ethics. For Bohr, science was a human endeavor, not a machine of knowledge, but a dialogue with nature. Today, when we look at diagrams of atoms in textbooks, the little circles and dots may seem simple, even naive, but behind those drawings lies a revolution. The moment when the universe revealed that stability is born from quantization, that light and matter speak in discrete notes. That revelation began with a quiet man in Copenhagen who dared to ask why atoms do not collapse. And so, the world before Bohr faded into history, replaced by a deeper, stranger, more beautiful vision of existence. From that vision came every modern advance in quantum science, from transistors to lasers to the exploration of the cosmos itself. His discovery reminds us that simplicity can hide the profound, that the universe, when explained in simple words, still glows with infinite wonder. In the early years of the 20th century, physics was in a quiet crisis. To the outside world, it looked like a golden age. The universe seemed neatly explained by the equations of Newton and Maxwell. Engineers were building machines, lighting cities, sending signals across oceans. The mechanical worldview appeared complete. Yet beneath this confidence, something was breaking. In laboratories across Europe, new experiments were uncovering patterns of light and energy that refused to obey the old rules. The pillars of classical physics were trembling, not from noise, but from the whisper of a new kind of truth. And into this world stepped Niels Bohr, a man who would listen to those whispers and translate them into the language of the atom. Bohr did not invent quantum theory. That seed was planted years earlier by Max Planck, almost reluctantly. When Planck studied the spectrum of radiation emitted by hot objects, what physicists call blackbody radiation, he faced a dilemma. According to classical theory, such an object should emit infinite energy at high frequencies, a clear impossibility. Planck tried every formula he could imagine, but none fit the experimental data until he introduced an audacious assumption that energy is not continuous but comes in discrete chunks, or quanta. It was a mathematical trick, he thought, a desperate fix, not a revolution. But his constant H became the heartbeat of all quantum theory. A few years later, Albert Einstein took Planck's idea further and made it real. In 1905, he published a paper explaining the photoelectric effect, the strange observation that light shining on metal can eject electrons, but only if the light's frequency is above a certain threshold. Classical wave theory could not explain this. Einstein proposed that light behaves as if it were made of particles, each carrying energy proportional to its frequency, E equal to Na. These particles, later called photons, were not just mathematical abstractions, they were real quanta of light. With this, Einstein had revealed that even light, the most continuous and wave-like phenomenon known, was granular at its core. For most physicists of the time, these ideas were fascinating but deeply uncomfortable. They challenged the smooth logic of classical mechanics. Even Planck himself resisted Einstein's interpretation of light as particles. The world had spent centuries believing in continuity. The idea of discontinuity felt like a step backward into mystery. Yet for Bohr, who came of age in the midst of this turbulence, these ideas were not threats. They were clues. By 1912, Bohr had absorbed both the old and new ways of thinking. He knew Newton's mechanics by heart. He could manipulate Maxwell's equations of electromagnetism with ease. But he also sensed that nature was whispering something beyond them. The stability of atoms, the pattern of spectral lines, the strange behavior of energy, all pointed to an unseen structure, one that could not be captured by continuous motion. To Bohr, Planck, and Einstein had given the first glimpses of that hidden architecture. They had shown that energy itself might be quantized, and that matter and radiation shared a deep connection. What remained was to weave these insights together into a coherent picture of the atom. Bohr's approach was unlike anyone else's. He did not simply add new assumptions to the old equations. He tried to reimagine what it meant for something to exist at the atomic scale. When he studied Rutherford's nuclear model, he saw its elegance and its failure. The nucleus provided a center, but the electrons, spinning around it under classical laws, should radiate energy and collapse. Yet if energy were quantized, perhaps radiation did not occur continuously. Perhaps electrons could occupy certain orbits where no energy loss happened, states of perfect stillness amid motion. He took inspiration directly from Planck's formula. If energy could only change in discrete multiples of hnu, then maybe the energy of an electron's orbit was similarly quantized. That simple analogy became a bridge. The electron's energy would not vary smoothly as it circled the nucleus, but exist in steps, like rungs on a ladder. When the electron jumped from one rung to another, it would emit or absorb a photon with energy equal to the difference between the two levels. Einstein's photons became the messengers between these energy states. The atom was no longer a machine leaking radiation, but a harmonious system exchanging quanta of light. It was this act of connection, Planck's quantization of energy, Einstein's light quanta, Rutherford's nucleus, that made Bohr's insight revolutionary. He was not solving a single problem, but uniting three separate discoveries into one consistent vision. And he did it not by clinging to logic, but by trusting intuition. In later years, Bohr would say that progress in science often requires us to abandon what we think we understand and accept paradox as the price of truth. He realized that Planck's constant, that tiny symbol h, was more than a number. It was the fingerprint of nature's discreteness. Everything that changed energy did so in multiples of h. It was as if the universe spoke a digital language long before humanity invented computers. Energy did not flow like water, it ticked like a clock. In the world of atoms, there were no fractions of motion, only allowed states separated by quantum leaps. To Bohr, Einstein's idea of light quanta offered a perfect metaphor for what might happen inside the atom. Just as light existed in packets, perhaps the electron's own energy was similarly quantized. Each orbit corresponded to a whole number of Planck's units. Radiation occurred only when the electron changed its state, emitting or absorbing a photon whose energy matched that difference. Suddenly, the patterns of light emitted by hydrogen, the mysterious spectral lines, became understandable. Each line represented a specific quantum jump. But Bohr's genius was not only in connecting ideas, it was in daring to defy reason where reason had failed. Classical physics demanded that acceleration produce radiation, that an orbiting electron must lose energy. Bohr said no. In certain orbits, the electron simply doesn't radiate. It was a rule without precedent, justified not by derivation but by necessity. He trusted the consistency of the phenomena more than the consistency of old logic. The atom was telling him how it behaved, and he listened. His insight did not come all at once. Letters from that time show him wrestling with equations, sometimes doubting himself, other times exhilarated. He wrote to Rutherford that perhaps the atom's stability was due to a new law of nature, one not yet formulated. He discussed with colleagues how Planck's energy elements could be applied to motion itself. Slowly, over months, the pieces aligned. The quantization of energy, the emission of photons, the stationary states, all combined into a framework that would explain hydrogen's spectrum with astonishing precision. When he finally published his theory in 1913, it was met with both wonder and disbelief. How could something so abstract, so discontinuous, describe reality? Yet the agreement with experiment was undeniable. Bohr had predicted the exact wavelengths of hydrogen's spectral lines, matching data that had puzzled scientists for decades. The beauty of it was overwhelming. The colors of light emitted by atoms were no longer random. They were the fingerprints of quantum transitions. Behind that achievement was a deeper philosophical leap. Bohr had connected not just equations but principles. Planck had shown that nature limits energy exchange. Einstein had shown that light itself is quantized. Bohr showed that matter obeys the same rule. The universe, from photons to electrons, was governed by discrete acts of transformation. Continuity was an illusion born of scale. At the smallest levels, reality pulsed in finite rhythms. He had also connected two seemingly opposite domains, radiation and matter. For centuries, light and substance were treated as distinct categories, one wave-like, the other material. But Bohr's model implied that the same quantum principle shaped both. Matter could emit light, because both obeyed the same quantized structure. This unity hinted at something profound, that the laws of energy are universal, binding all forms of existence into a single system. In a sense, Bohr's discovery was not a calculation but a revelation. It required the courage to let go of common sense and accept a world where electrons jump between invisible levels and light travels in packets. To most people, such behavior sounded magical, but to Bohr it was simply how nature maintained harmony. He believed that the universe is not random but ordered in ways that transcend human intuition. The atom was not chaotic, it was precise, mathematical, and strangely beautiful. The connection between Bohr, Planck, and Einstein was more than intellectual, it was generational. Planck was the cautious pioneer, Einstein the daring visionary, and Bohr the architect who built the first structure of quantum theory from their stones. Without Planck's constant, there would be no quantization. Without Einstein's photons, there would be no explanation of radiation. Without Bohr, there would be no atomic model uniting them. Together, they transformed the world's understanding of energy, light, and matter. Bohr's model also gave scientists a new way to think about information. Each transition between energy levels carried data about the structure of the atom. Every photon emitted was a message, encoded with the difference between two quantized states. The universe was communicating through light, and humans were finally learning to read its language. By connecting quantum theory to atomic structure, Bohr did something more than explain a mystery. He redefined what explanation itself meant. Classical science described how things moved. Quantum science described how things could exist. The atom did not behave according to continuous laws because the universe at that scale was not continuous. It was built from possibilities, not certainties. In Copenhagen, Bohr often spoke softly about these ideas to his students, emphasizing that understanding was not about pictures, but about principles. He told them that the human mind must learn to see in quanta, to think in jumps rather than flows. Nature, he said, allows only specific questions and gives specific answers. To go beyond that is to demand of reality what it does not contain. This humility before the unknown became a hallmark of Bohr's philosophy. As he connected the discoveries of Planck and Einstein, Bohr began to glimpse something larger than physics itself, a philosophy of existence. The quantization of energy was not just a property of matter, it was a pattern of reality, discreteness, uncertainty, complementarity. All these ideas would later grow from this seed, but in that early moment of insight it was simple. The atom stands stable because energy comes in steps. Stability is not an accident, it is a consequence of quantization. In those years, as Europe stood on the edge of war, Bohr worked quietly, his thoughts detached from the chaos of politics. Yet what he was building would change not just science but technology, philosophy, and even the way humans saw themselves. The connection he forged between light and matter would lead, in time, to everything from lasers to quantum computers, from atomic clocks to the understanding of stars. The energy that glows in every lamp, every screen, every distant sun, all speaks the same quantum language, that Bohr helped decode. And yet, when he first saw the equations balance, when the numbers matched the spectra, his feeling was not triumph but awe. He had glimpsed the simplicity behind the complexity, the order behind the apparent chaos. Nature, it seemed, was whispering in a dialect of mathematics and light. Bohr's mind, tuned by patience and curiosity, was the first to truly listen. The year 1913 would be remembered as a quiet turning point in the story of human understanding. Europe was tense with politics and invention, but in the small world of physics, a deeper revolution was brewing, one that would not break cities but change thought itself. Bohr's papers on the atom had begun circulating, typed in modest fonts, sent by mail to colleagues across the continent. Inside those pages lay the first true connection between the mysteries of light and the architecture of matter. To many who read them, it felt as if a curtain had been drawn back on the invisible. For the first time, scientists could read the secret language that joined the sunbeam and the substance of their own hands. Bohr had taken Planck's constant, that tiny, almost mystical number, and built an entire world upon it. In Planck's time, H was a reluctant invention, a patch to fix an equation. In Bohr's hands, it became the grammar of reality. He used it to describe how electrons could possess only certain energies, each corresponding to an integer multiple of h divided by 2p. A new constant he called h. The simplicity of it was breathtaking. With a single assumption, the impossible stability of atoms made sense. But behind that simplicity lay a vast philosophical shift. Energy was no longer a smooth landscape, it was a staircase, and every movement of light or matter was a step. Bohr's insight showed that the laws Planck had used for radiant heat and the laws Einstein had used for light quanta were not isolated phenomena, but reflections of one principle. Energy itself was quantized. Whether in radiation or in orbit, when a metal glowed red, when a gas emitted blue light, when the stars burned across the night sky, each event was a conversation between quanta of matter and quanta of light. The universe was speaking in discrete notes, and Bohr had tuned his ear to hear them. At first, few people could believe it. Rutherford admired Bohr's courage, but admitted he didn't understand how electrons could leap without traveling. The idea of quantum jumps sounded more like magic than physics. Even Einstein, though intrigued, questioned whether such discontinuities could be real. But Bohr trusted the harmony between theory and observation more than his own instinct for logic. Nature, he said, is not obligated to follow our reasoning. Our reasoning must follow nature, and nature was unambiguous. The spectra of hydrogen matched his formula exactly. Those spectral lines were more than colors, they were proof. Each bright band was a photon released when an electron fell from one allowed orbit to another, carrying away the precise energy difference between the two states. It was Einstein's photoelectric effect in reverse. Instead of light freeing electrons, electrons were creating light. In that exchange, the worlds of Planck and Einstein met perfectly, unified by Bohr's architecture of the atom, the effect on the scientific. Imagination was electric. Suddenly it became clear that quantum theory was not just a curiosity of heat or light, but the foundation of all atomic structure. Matter itself was quantized. The familiar solidity of the world rested on the invisible rhythm of Planck's constant. Every color, every chemical reaction, every bond that held a molecule together was governed by these same tiny steps of energy. Bohr's model transformed physics from the study of motion to the study of transitions. But Bohr did not stop at hydrogen. He wondered whether the same principles could explain the behavior of larger atoms and molecules. Could the periodic table, that elegant pattern of elements, be understood as a hierarchy of quantum orbits? He suspected it could, though the mathematics soon grew complex. Yet the idea was powerful enough to inspire a generation of scientists. In Göttingen, Sommerfeld refined Bohr's orbits, introducing elliptical paths and additional quantum numbers. In Munich, Pauli would later use these numbers to describe the exclusion principle that determines how electrons fill shells. All of modern chemistry unfolded from that lineage, all tracing back to the moment when Bohr dared to connect the quanta of light to the orbits of electrons. Still, Bohr's connection to Planck and Einstein went deeper than equations. It was also philosophical, a dialogue about what could be known. Einstein's photon concept implied that nature behaved as if particles and waves were two sides of one reality. Bohr embraced that paradox rather than rejecting it. He began to see complementarity everywhere: wave and particle, continuity and discontinuity, determinism and probability. He believed that these opposites were not contradictions but partners, each revealing part of a truth that could not be captured by either alone. This way of thinking became the soul of the quantum era. The elegance of Bohr's theory lay in its restraint. He did not try to describe what the electron was doing between orbits. He admitted that such a question might be meaningless. Physics, he said, should describe what we can observe, not what we imagine between observations. When an electron emits a photon, we see the before and after. The in-between is nature's secret. This humility before the limits of knowledge was revolutionary. It freed science from the illusion of total comprehension and replaced it with a disciplined wonder. As the model gained fame, young scientists flocked to Copenhagen to meet the man who had bridged the gap between Planck's quanta and Rutherford's nucleus. They expected a prophet of certainty but found a philosopher of patience. Bohr listened more than he spoke, often pausing for long moments before answering, as if testing whether words themselves could carry quantum precision. He reminded his visitors that every explanation is provisional, every model a metaphor. What mattered was not to freeze knowledge, but to let it evolve, as the atom itself does, through transitions. The connection between Bohr, Planck, and Einstein also transformed the understanding of energy conservation. In classical physics, energy flowed continuously. In Bohr's world, it was exchanged in exact quanta, but the total always remained constant. Each photon emitted carried away just enough energy to balance the electron's fall. This gave the conservation law a new quantum form, a balance of discrete transactions. Energy, it turned out, was not a river, but a series of perfectly counted coins. The economy of nature was exact. As more evidence accumulated, Bohr's model began to shape practical science. Spectroscopy became a precise tool for identifying elements in stars and gases. Astronomers, using telescopes and prisms, could now decode the composition of distant suns by their spectral fingerprints. Every stripe of color across a spectrograph became a direct signature of quantum transitions. The cosmos itself was revealed as a vast collection of atoms obeying Bohr's law. Even the light of the Milky Way whispered of quantized orbits. Bohr's achievement also deepened the mystery of matter. If electrons moved only in allowed states, what determined those states? Why did Planck's constant have the value it did? What gave the universe its scale of discreteness? These questions still haunt physics today, but in Bohr's time they were exhilarating. They hinted that beneath the apparent randomness of nature lay an intricate design, not mechanical but mathematical. It was as though creation itself were written in the language of quanta. As Einstein developed his theory of relativity, he and Bohr found themselves representing two different visions of nature: Einstein's continuous space-time and Bohr's discrete quantum world. Yet Bohr never saw them as enemies. He admired Einstein profoundly and often said that the relativity principle and the quantum principle were complementary. Two great harmonies of the same universe. In letters between them, one senses both affection and friction. Einstein questioning the completeness of quantum theory, Bohr replying that completeness is not for humans to demand, but for nature to define. Their friendship was an ongoing experiment in humility and genius. The fusion of ideas from Planck, Einstein, and Bohr did not stop with atomic theory. It opened the door to technologies no one could have imagined. The quantization of energy underlies everything from the color of LEDs to the precision of atomic clocks. Each of these marvels traces its ancestry back to the realization that energy comes in discrete steps. A principle that began with Planck's blackbody studies, was illuminated by Einstein's photons, and was crystallized in Bohr's atom. What made Bohr unique was his ability to balance boldness with caution. He built on Einstein's daring but grounded it in calculation. He respected Planck's mathematical discipline, but expanded it into a new vision. Where others saw contradictions between particle and wave, Bohr saw dialogue. He turned conflict into complementarity, showing that truth could be larger than logic. In his world, an electron could be both a wave and a particle, Because human language had reached its limit, only mathematics could express the full reality. His model was not the end of understanding, but the beginning of humility. When he looked back on his youth, Bohr described those years as a time of constructive confusion. The universe was teaching physicists to think differently, to replace certainty with probability, continuity with quanta. To connect Planck and Einstein to atomic structure was to accept that knowledge grows by contradiction. Each discovery refutes part of what came before, but preserves its essence in a higher order. Bohr believed this was not only how science evolves, but how consciousness itself expands. In later years, as quantum mechanics matured, Bohr's original model was refined and replaced by wave equations and probability clouds. Yet every student of physics still begins with the Bohr atom, that small solar system of quantized orbits, because it captures the essential poetry of discovery. It tells the story of how three minds, Planck, Einstein, and Bohr, spanned the gap between heat, light, and matter to reveal a universe that pulses in discrete beats. The simple image of an electron leaping between orbits became a metaphor for human thought. Knowledge itself advances in quantum jumps, sudden transitions after long periods of stillness. One moment the world seems complete, the next a single insight rearranges everything. Bohr's moment of insight was exactly that kind of leap. He did not crawl from the classical to the quantum, he jumped, guided by faith in consistency and simplicity. In that leap he carried with him the legacies of Planck and Einstein, transforming isolated curiosities into a coherent vision of the atom. Today, more than a century later, the echoes of that connection still shape the frontiers of science. Quantum computers manipulate qubits that exist in superpositions, a direct descendant of Bohr's complementarity. Photonics, lasers, and semiconductors all rely on the quantized interactions he described. When we split light into photons or trap atoms in magnetic fields, we are repeating the conversation that began between Planck's furnace, Einstein's light, and Bohr's imagination. If we could travel back to that small office in Copenhagen, we would find Bohr surrounded by chalk dust and quiet concentration. The afternoon light slanting through the window, the equations half erased on a blackboard. He would be pacing slowly, murmuring to himself about energy levels and quanta, pausing to draw a tiny circle that represents an electron's orbit. To an outsider, it would look simple, almost childlike. Yet in that simplicity lay the structure of existence. Every atom in the universe obeyed that same law. Every star, every breath, every spark of electricity followed the rhythm Bohr was uncovering. He would later say that understanding is a series of approximations. Theories are not mirrors of nature, but instruments for exploring her music. The connection he made between Planck's quantization, Einstein's photons, and the atom's structure was one such instrument, perhaps crude by modern standards, yet tuned so perfectly to its time that it changed the melody of science forever. By 1920, Bohr's name was known throughout the scientific world. Students memorized his formulae, professors debated his postulates, and the public marveled at the idea that reality itself could be granular. The atom, once imagined as an indivisible particle, had become a tiny, quantized universe. And at its heart stood the constant H, Planck's silent signature, Einstein's light quanta, and Bohr's orbits all woven together. In the end, Bohr's greatest contribution was not merely the model but the mindset it inspired. He showed that progress comes from synthesis, from listening to the faint harmony between seemingly opposed truths. The moment of insight that defined his life was born not from invention, but from connection, from seeing how the discoveries of others formed a pattern larger than any one of them could see. It was as if nature had left fragments of a message with Planck and Einstein, and Bohr was the one who finally assembled them into a sentence, and that sentence, once spoken, changed everything. It told humanity that the universe is not continuous and predictable, but rhythmic and quantized, that energy moves in jumps, light travels in quanta, and stability arises from discontinuity. It told us that even in the smallest atom lies a reflection of the cosmic order. Through Bohr's eyes, the world became a dance of discrete possibilities, a universe that flickers between states but never loses its harmony. Thus ended the first great chapter of the quantum story, a story born of Planck's furnace, illuminated by Einstein's photons, and given form in Bohr's atom. From that foundation, the future of physics would unfold like light itself, in quanta, one leap at a time. When the world first heard of Niels Bohr's atomic model, it was as if a fog had lifted from one of nature's most profound mysteries. The atom, that tiny and invisible unit of matter, had been a subject of fascination and confusion for centuries. Philosophers had guessed at its existence, chemists had used it as a concept, and physicists had tried to model it, but until Bohr, no one had succeeded in giving it both structure and stability. His model, simple yet revolutionary, described electrons not as random wanderers, but as disciplined travelers moving in precise, quantized orbits, paths that could be drawn, calculated, and understood. It was a new image of matter, a cosmic miniature of order inside chaos. To appreciate what Bohr achieved, one must imagine the scene before his arrival. The atom was thought to be like a tiny solar system. Rutherford had already revealed that almost all of an atom's mass was concentrated in a dense nucleus, with electrons orbiting it like planets around the sun. It sounded beautiful, but there was a fatal flaw. It couldn't work. According to classical physics, any charged particle moving in a circle would constantly lose energy as radiation. An orbiting electron should emit light, lose speed, and spiral into the nucleus within a fraction of a second. If that were true, every atom in the universe would collapse instantly. And matter would not exist, but matter did exist. Solid, stable, enduring. The classical laws had failed. Bohr realized that the failure was not in the mathematics, but in the assumptions behind them. He asked a daring question. What if electrons did not move freely as classical mechanics demanded? What if their motion was restricted, allowed only in certain specific orbits? He imagined the atom as a system of discrete energy levels, each corresponding to a specific orbit around the nucleus. An electron in one of these orbits could remain there indefinitely without radiating energy. Radiation, he proposed, occurred only when the electron jumped from one orbit to another, emitting or absorbing a photon whose energy equaled the difference between the two orbits. In one elegant stroke, he had explained both atomic stability and the mysterious spectra of elements. In Bohr's model, the orbits were not arbitrary. Each orbit corresponded to a specific energy determined by Planck's constant, the same number that Planck had discovered in blackbody radiation, and Einstein had used for photons. Bohr proposed that the angular momentum of an electron, the measure of its rotational motion, was quantized. In simple terms, this meant that the electron could not spin around the nucleus at just any speed or distance. Only those orbits where the angular momentum equaled an integer multiple of h2pi were allowed. If it tried to exist in between, nature simply forbade it. It was as if the atom contained invisible rails, and the electron could move only on those rails, never in between. This idea may sound abstract, but its implications were concrete and stunning. For the hydrogen atom, the simplest of all, Bohr calculated the allowed orbits and found that the energies matched perfectly with the observed spectral lines. When the electron fell from a higher orbit to a lower one, it emitted light of a precise color, corresponding to the exact energy difference between those levels. The Balmer series, a pattern of spectral lines that had puzzled scientists for decades, was suddenly explained in full. The atom, once chaotic and mysterious, became a structured, quantized machine of elegance and precision. Bohr's model painted a picture of the microscopic world that was as orderly as the celestial one. Yet it was not the same order as Newton's. It was a new kind, one built from restrictions, from possibilities and impossibilities rather than from continuous freedom. The electron, once imagined as a tiny planet, was now more like a musician confined to specific notes on a cosmic instrument. It could not play in between, it could only jump from one note to another, and the light it emitted was the song of that jump. This model turned the atom into something that could be visualized and calculated, something both poetic and precise. It told scientists that nature was not chaotic but quantized, structured in discrete steps. The electron's orbit was defined not by chance but by necessity. The radius of each orbit, the energy of each level, the frequency of each photon, all could be computed with exact mathematical expressions. For the first time, theory and experiment agreed not just approximately, but perfectly. The colors of hydrogen's light, measured with delicate instruments, matched Bohr's formulae to the last decimal. It is difficult now, in our age of quantum familiarity, to grasp how radical this was. Before Bohr, no one had seriously imagined that motion itself could be quantized. Planck had quantized energy exchange, Einstein had quantized light, but Bohr quantized the very act of movement within the atom. He showed that the structure of matter was governed by discontinuities, that the electron's energy was not a smooth gradient, but a set of fixed rungs. It was as if nature had built ladders inside every atom, and electrons could only stand on the rungs, never on the rails between them. To understand how this worked, imagine the atom as a small, invisible solar system. In the center sits the nucleus, dense and positively charged. Around it, electrons travel in circular orbits, but not any orbits, only those permitted by quantum rules. Each orbit corresponds to a specific energy level. The farther the orbit from the nucleus, the higher the energy. The electron in the lowest orbit is said to be in the ground state, stable and quiet. If energy is added, say by heating or electrical discharge, the electron can jump to a higher orbit, an excited state. But this excitement is temporary. The electron soon falls back, releasing the absorbed energy as a photon, a flash of light. The color of that light depends entirely on the energy difference between the two orbits. Every atom, therefore, has its own signature, its own spectral fingerprint. Bohr's model explained this perfectly. What made Bohr's theory so compelling was not just its success with hydrogen, but its conceptual simplicity. It didn't require any unknown forces or complex assumptions. It took existing ideas, the nucleus from Rutherford, quantization from Planck, and photons from Einstein, and combined them into a single picture. It was like discovering that three scattered puzzle pieces, once placed correctly, revealed the whole image. Bohr's genius lay in seeing the pattern no one else saw. The effect of his model rippled far beyond atomic physics. It redefined what understanding meant in science. Before Bohr, understanding meant tracing every movement, knowing every trajectory. After Bohr, understanding meant recognizing the limits of motion and the discrete laws that governed it. It was a humbling shift. From control to comprehension, from prediction to probability, the atom could not be described as a miniature solar system obeying Newton's laws. It was a quantum organism, alive with jumps and pauses, ruled by a logic all its own. Bohr's orbit soon became iconic. Textbooks were filled with diagrams showing tiny circles labeled n, equal to 1, 2, 3, and so on. The quantum numbers representing allowed energy levels. Students could calculate the radius of each orbit, the energy required to excite an electron, and the frequency of the emitted photon when it returned. The simplicity was astonishing. One small equation, equal to 13.6 eV 2 En, equal to 13.6 eV Ni 2, captured the entire hydrogen spectrum, but the simplicity hid a deeper mystery. What was the electron actually doing between orbits? Was it moving like a planet or vibrating like a wave? Bohr's model didn't say, and that silence was deliberate. He understood that classical images could only go so far. The orbit was not a literal path in space, but a symbol, a way of expressing quantized energy in familiar terms. The atom was not a mechanical object, but a mathematical one. The world embraced the Bohr model, not because it explained everything, but because it explained enough to guide the next generation of discoveries. It became the seed from which modern quantum mechanics would grow. Schrödinger would later replace Bohr's orbits with wave functions, and Heisenberg would replace them with matrices, but both would keep Bohr's central idea, that electrons exist in quantized states and that transitions between them produce light. In that sense, the Bohr model is not obsolete. It is eternal. It marks the moment when humanity learned that the building blocks of the universe are governed by numbers, not by motion. Bohr's visualization of specific orbits also transformed chemistry. It gave a physical meaning to the periodic table. The arrangement of elements, their reactivity, valence, and bonds, could now be traced to the structure of their electrons. Each atom's chemical behavior depended on how its electrons filled these quantized orbits, or shells. Hydrogen, with one electron, occupied only the first shell. Helium filled it completely and became stable. lithium began the second shell. Thus, Bohr's atomic model bridged physics and chemistry, uniting the two sciences under a single quantum roof. Beyond the laboratory, the image of Bohr's atom captured the public imagination. Newspapers illustrated it as a miniature solar system, with tiny planets spinning around a radiant core. It became the emblem of modern science, a symbol of order hidden inside chaos, simplicity behind complexity. Artists, poets, and philosophers seized on it as a metaphor for the unity of the cosmos. For the first time, the atom was not a mystery to fear, but a marvel to admire. Yet Bohr himself was cautious about such visualizations. He knew they were only approximations, metaphors for the mind, not mirrors of reality. The electron's orbit was not a path you could draw, but an expression of quantized energy. Still, he allowed the diagrams to flourish because they served as bridges between intuition and truth. To understand the atom, people needed an image, even if that image was only a shadow of the real thing. Behind Bohr's calm explanations lay an awareness of something profound. The laws of the microscopic world were not just different from the macroscopic ones, they were opposite. In the large world, motion is continuous. In the small world, it is discontinuous. In the large world, energy can vary smoothly. In the small world, it changes in jumps. In the large world, certainty is possible. In the small, only probability. The Bohr model was the first doorway into that paradoxical realm, and perhaps that was Bohr's greatest insight, that electrons do not wander randomly but move within boundaries defined by quantization. The universe, at its most fundamental level, is disciplined. It allows freedom, but only within certain rules. Those rules are the grammar of creation. Bohr's atom gave humanity its first clear sentence in that language. As word of Bohr's atomic model spread through the scientific community, it was as if a new map of reality had been drawn. Men who had spent their lives staring into spectroscopes, cataloging endless bright and dark lines, now saw meaning where there had only been mystery. Every streak of color was the voice of an electron, every gap between lines a silence dictated by forbidden orbits. Nature, once mute in its smallest scales, was suddenly articulate, and the language it spoke was quantization. Bohr's diagrams appeared in journals and lectures, circles within circles, each labeled with an integer, n equal to 1, n equal to 2, n equal to 3. They were modest drawings, but behind them lay an entire universe of precision. Each number described not only a distance from the nucleus, but a specific energy. The smallest orbit, n equal to 1, held the electron closest and bound most tightly. The higher the number, the looser the bond, until at last the electron could break free entirely. Ionization. That simple sequence explained why atoms could absorb only certain amounts of energy, why heating a gas or striking it with electricity produced distinct spectral patterns instead of continuous rainbows. The atom had rhythm, to a generation raised on Newton's seamless clockwork. The idea that an electron could exist only on quantized tracks was shocking. How could motion itself be restricted? Yet Bohr's model demanded it, and experiment confirmed it. When scientists tested hydrogen's emission and absorption lines with ever finer instruments, the results marched in lockstep with his predictions. There was no smooth continuum of color, only discrete, perfect frequencies like keys on a cosmic piano. Each photon corresponded to a precise jump from one orbit to another. It was music written in light. Bohr often said that the purpose of science was not to remove wonder but to make it intelligible. His atom embodied that philosophy. It was simple enough to draw on a blackboard, yet deep enough to sustain decades of discovery. Its orbits gave physicists a way to measure and imagine, and gave philosophers a reason to question what real meant. Was an electron truly circling like a planet, or was that just a convenient picture for the human mind? Bohr knew the answer was both yes and no. The orbit existed only in calculation, not in space. Between observation and reality there lay a gap that no equation could cross. Still, the model worked, and that was enough. In laboratories across Europe and America, researchers used Bohr's formulae to calculate the energies of different atoms. For hydrogen, it was exact. For helium and heavier elements, approximations were needed, but the principle held. The periodic table, once a chemical curiosity, began to reveal its quantum skeleton. The number of electrons in each shell determined how elements bonded, why sodium exploded in water while neon refused to react, why gold shone yellow and copper red. Chemistry, long an empirical art, found its theoretical heart in Bohr's orbits. He had done more than explain a spectrum. He had united physics and chemistry into a single vision of matter. The Bohr model also transformed our understanding of stability. Before him, the atom was a paradox, charged particles attracting and repelling in an apparent stalemate. After him, stability became natural, a consequence of quantum law. The electron did not collapse into the nucleus because there was no lower allowed orbit to fall into. It was confined by the very discreteness of energy. Nature's smallest parts obeyed rules that prevented chaos. In that revelation lay something almost philosophical. Order is not imposed on the universe, it is built into its fabric. Yet Bohr was never satisfied with easy triumph. He knew his model was provisional, a bridge between the old world and the new. When colleagues pressed him about what an electron actually did between jumps, he smiled and said that perhaps the question had no meaning. The atom, he explained, was not a miniature mechanism but a system defined by what could be observed. When an electron emitted light, we saw two states, before and after, and a photon connecting them. The in-between was not part of observable reality. It was a concept from the classical past, useful but misleading. To ask what happened during the jump was like asking where a melody goes when the musician pauses. This cautious realism would become the foundation of the Copenhagen interpretation years later, but its seeds were already here. Bohr's model was not only a description of atoms, it was a lesson in epistemology, a demonstration that knowledge is shaped by the questions we are able to ask. The quantized orbits were not lines in space, they were boundaries of comprehension. Still, the image of tiny planets circling a nucleus proved irresistible. Artists painted it, publishers printed it, and school children memorized it. The atomic symbol, a nucleus orbited by rings, soon appeared everywhere, on scientific societies' logos, on postage stamps, on the emblems of universities and space agencies. Even though later physics would replace orbits with probability clouds, the old picture endured because it captured the imagination. It made the invisible tangible, and it carried within it the essence of Bohr's discovery. That the universe, even at its smallest, is structured. In those years following 1913, Bohr's life was a storm of correspondence and debate. Letters arrived daily from scientists across Europe. Sommerfeld in Munich, born in Göttingen, Millikan in Chicago, each with new data or new questions. Bohr responded with humility and patience. He corrected errors, acknowledged limitations, refined constants. He never claimed his model was the final word. Every great and deep difficulty, he wrote, bears in itself its own solution. The Bohr model was one such difficulty resolved, and at the same time a doorway to even greater mysteries. One of those mysteries concerned why electrons should prefer these quantized paths. What force selected them? Classical mechanics could not answer. It would take the wave mechanics of Schrödinger and the uncertainty principle of Heisenberg to explain that the allowed orbits correspond to standing waves, configurations in which the electron's wave function fits perfectly around the nucleus, reinforcing itself. But that insight lay a decade ahead. In 1913, Bohr could only intuit that something deeper than mechanics was at play. He trusted his intuition because it matched the evidence. He often said that the task of science is not to find final truths but to find relations that remain consistent. As physicists applied Bohr's ideas to other systems, they found patterns everywhere. Spectra of helium, lithium, sodium, all showed quantized features. Even in solid materials, electrons seem to occupy discrete energy bands, giving rise to conductivity, magnetism, and the color of metals. Bohr's principle of quantized states became a universal tool. It was the first thread of what would later become quantum mechanics proper. His orbits were like the scaffolding of a new building, temporary yet essential for the structure to rise. The simplicity of Bohr's atom also inspired the broader culture. Poets compared it to a miniature cosmos, theologians to the harmony of creation. The idea that order could emerge from restriction, that freedom itself could exist only within quantized boundaries, resonated far beyond physics. In a world heading toward war and chaos, Bohr's calm model of balance felt almost moral. It suggested that even in turmoil there is an underlying logic, that the universe itself is built on stability through limits. Bohr, however, never sought symbolism. He worked quietly, always refining details, guiding students, and encouraging debate. He welcomed disagreement, even enjoyed it, for he believed that contradiction was the engine of progress, the opposite of a profound truth. He would later say, may well be another profound truth. That paradox lay at the heart of his atomic vision. The electron was both motion and rest, both wave and particle, both bound and free. To capture its reality, one had to accept that opposites could coexist. His colleagues soon recognized that the Bohr model was more than a step forward, it was a change in direction. It pointed science toward a future where equations would describe probabilities rather than certainties, where observation would shape outcome, where energy and matter would blur into information. All of that began with the simple idea that electrons travel in specific orbits instead of random paths. Decades later, when quantum mechanics replaced those orbits with orbitals, fuzzy clouds of likelihood, physicists did not discard Bohr's model. They honored it as the first true bridge between the seen and unseen. In every modern textbook, it still stands as the entry point into the quantum world. The rings may be symbolic, but the quantization they represent is real. Every laser pulse, every semiconductor, every atom trapped in a quantum computer still obeys Bohr's principle. Electrons occupy discrete energy levels, and transitions between them release or absorb exact quanta of light. When Bohr looked at the atom, he saw not chaos but design, not randomness but rhythm. To him, the universe was not a storm of particles but a symphony of states. Each electron moved within the measure of Planck's constant, each orbit a note in the music of existence. It is no exaggeration to say that this vision reshaped how humanity imagines reality itself. The mechanical universe of Newton gave way to the quantized universe of Bohr, where certainty yielded to structure and continuity to cadence. In quiet moments, Bohr admitted that he found beauty more convincing than logic. His model was beautiful because it worked with minimal assumptions. It restored order where theory had failed, not by adding complexity, but by revealing simplicity hidden beneath confusion. The atom, once imagined as chaotic, became the most orderly thing in nature, a geometry of light and motion, balanced by quantum law. From that order would arise the modern world. Electricity, electronics, chemistry, and, ultimately, the digital age. He could not have known how far his idea would reach. When transistors were invented, when lasers were built, when computers began to hum, each relied on the quantized orbits he had first described. Even today, when scientists manipulate individual atoms to store information, they are still following Bohr's map, the ladder of discrete energy states, the rules of allowed transitions. The orbits may have dissolved into probability clouds, but their essence remains. In the grand sweep of history, Bohr's model stands as a turning point equal to Copernicus's heliocentric system. Copernicus moved the Earth from the center of the cosmos. Bohr moved certainty from the center of science. He showed that the universe is not continuous but quantized, not predictable in every detail but reliable in its laws. The orbits he drew were more than paths for electrons. They were boundaries of human understanding, the limits within which knowledge itself could safely move. Even at the end of his life, when quantum mechanics had long surpassed his early model, Bohr spoke of it with affection. It had been his first glimpse into the heart of mystery, the first time he had heard the whisper of the quantum world. The electron's orbit, he said, is like a word in a language we are still learning to speak. Each discovery adds another syllable, another meaning, but the grammar remains the same, the grammar of quantization. So when we picture the atom, a small nucleus surrounded by rings of electrons, we are not looking at literal truth, but at an idea that changed the world. Those rings are the memory of Bohr's leap of imagination, a symbol of how science advances, by daring to draw what cannot be seen, to impose simplicity where chaos appears. They remind us that the universe, even in its smallest scales, is ruled by harmony disguised as limitation. And that is the enduring gift of the Bohr model. It taught humanity that electrons do not roam aimlessly but travel in disciplined orbits, each defined by the laws of quantum mechanics. It taught us that stability comes from restriction, that light is born from leaps, that order is woven from discontinuity. It revealed that beneath the apparent randomness of the world lies a silent architecture, circles of probability, notes of energy, paths of meaning. To see that architecture is to glimpse the mind of nature itself. In the heart of Bohr's atomic vision lies one of the most breathtaking ideas in the history of science, the quantum jump. To the classical mind, movement was always smooth and continuous, like a planet circling the sun or a wave rolling across the sea. But inside the atom, Bohr discovered, motion is not a flow but a leap. Electrons do not slide gradually from one orbit to another. They vanish from one energy level and reappear in another, releasing or absorbing light in the process. It was an idea so strange that even physicists found it hard to imagine, yet it explained everything that the old theories could not: the stability of matter, the colors of elements, and the discrete patterns of light that form the atomic spectra. Bohr's quantum jump was not merely a mechanical description, it was a glimpse into the rhythm of the universe. When an atom absorbs energy, an electron leaps to a higher orbit, leaving the lower one empty for a brief invisible instant. When it returns, it releases that stored energy as a photon, a particle of light. The color of that light, its frequency, is determined exactly by the difference in energy between the two orbits. If the gap is large, the photon has higher energy. Perhaps in the ultraviolet range, if small, it glows red or yellow. Every element emits its own pattern of colors, a cosmic barcode by which scientists can identify it even in the light of distant stars. Those patterns, so precisely measured by spectroscopists, are the echoes of electrons leaping across invisible staircases of energy. This notion defied every intuition of the time. Nothing in everyday life behaves this way. You cannot leap between two floors of a building without passing through the space between, but electrons do exactly that. They jump without traversing. Bohr didn't claim to know how. He only knew that nature demanded it. He accepted that between those levels there is no intermediate state, no halfway position, no continuous path. The electron simply exists in one state or another, and the act of transition is instantaneous. It was not an act of imagination, but of courage, to believe the equations even when they contradicted reason. This single concept transformed physics. It revealed that energy is exchanged in packets, not flows, and that light itself is born from those packets. Every photon that strikes your eye, every glimmer from a distant star, is a record of one such quantum leap. The universe shines because its atoms are constantly dancing between energy levels, turning electrical potential into radiance. The stars twinkle not from chance but from the endless choreography of quantum jumps. What appears to us as a steady beam of light is actually billions of electrons falling back to lower orbits, each emitting a photon as pure as a heartbeat. For Bohr, this was not only a discovery but a revelation about how nature speaks. It showed that the microscopic world is not a smaller version of our own, but a domain ruled by its own laws, laws that ignore our logic yet obey their own perfect order. The quantum jump became a symbol of that order, sudden, exact, and irreversible. It explained why atoms emit sharp lines of color instead of continuous rainbows. The electron cannot release arbitrary amounts of energy. It can release only those differences allowed by its orbits. Nature is exact even in her leaps. In laboratories, this insight changed everything. Scientists could now calculate the energy of each transition, predict the color of emitted light, and even use it to measure distances in the universe. When astronomers looked at the spectra of faraway galaxies, they saw Bohr's principle written across the stars. Each line of color, stretched or shifted, told them the speed and composition of worlds they could never touch. The quantum jump connected the infinitely small with the infinitely large. Bohr's idea also hinted at something deeper about reality itself, that change does not always happen by degrees. Sometimes it happens by leaps, by discontinuities that redefine what came before. In the world of atoms, there is no sliding between states, only transformation. In the same way, human understanding too advances by jumps, sudden insights that shift our vision forever. The discovery of quantum jumps was such a leap in thought, a transition from the old classical orbit of certainty to the higher level of quantum awareness. Even now, the phrase quantum leap has entered language as a metaphor for radical change, but its origin remains literal and luminous. Every flicker of light around us is a living demonstration of that principle, from the glow of neon signs to the sparkle of the sun, from the fire of stars to the pulse of lasers. All of it comes from electrons, moving between quantized states, emitting photons with perfect precision. The quantum jump is the heartbeat of the cosmos, invisible but constant, the mechanism by which darkness becomes light. In simple words, Bohr discovered that when an electron jumps, the universe speaks, and that speech is light. The jump is the smallest event with the greatest consequence, the bridge between energy and perception, between matter and meaning. Every photon that touches our eyes, every color that paints our world, is a message from that unseen dance. The atom, in its silence, is never still. It is forever leaping, forever shining, and in those jumps lies the proof that even at the smallest scale, creation is not a flow but a miracle repeated trillions of times each second. The miracle of the quantum leap. Bohr's discovery did more than explain how electrons orbit the nucleus. It revealed why those orbits produce light in the exact way they do. The hydrogen atom, so simple that it contains only one electron, became the key to understanding all matter. Scientists had long noticed that when hydrogen gas is heated or energized, it emits light with very specific colors. When that light passes through a prism, it splits into sharp, distinct lines instead of a smooth rainbow. Each line represents a particular wavelength, a specific energy. Before Bohr, no one could explain why these lines existed or why they appeared at those precise intervals. His model provided the answer. They were the visible evidence of electrons jumping between energy levels inside the atom. When an electron in hydrogen absorbs energy, it leaps from its stable lowest orbit to a higher one. Farther from the nucleus, less tightly bound, it cannot remain there forever. The excited state is unstable. Sooner or later, the electron returns to a lower orbit, and in doing so it releases the difference in energy as a photon. The frequency of that photon, and thus its color, depends on the size of the energy gap between the two orbits. The greater the gap, the higher the frequency of the emitted light. This simple principle explained the entire hydrogen spectrum. Every line on the spectrogram, from the red glow of the Balmer series to the invisible ultraviolet and infrared bands, corresponded perfectly to the jumps between specific orbits. This was more than a triumph of calculation. It was the first time anyone had decoded the color signature of an element. Each spectral line became a fingerprint of that element's atomic structure, an unchanging identity card written in light. Hydrogen spectrum matched Bohr's formula with astonishing precision. When the same method was applied to helium, sodium, and other elements, the pattern held true. The quantum theory of orbits could predict exactly what colors an atom would emit or absorb. The invisible had become predictable, measurable, and real. The implications stretched across science. In laboratory spectroscopy, the study of light from atoms, became the most powerful tool for identifying elements. In astronomy, it became a window into the universe. By analyzing the light from stars and galaxies, scientists could tell which elements they contained, how hot they were, and how fast they were moving. The same patterns Bohr explained in a tiny hydrogen flame were visible in the hearts of distant suns. The atom and the cosmos were linked by the same law. When a star glowed, it was performing the same quantum dance as a lamp or a spark. The night sky was no longer silent. It was a grand spectrum, each color a note in a cosmic symphony of energy transitions. Bohr's theory also explained absorption, the dark lines seen when light passes through a cooler gas. Those lines occur because electrons in the gas atoms absorb photons of certain energies, jumping up to higher levels. Only the exact frequencies corresponding to those jumps are absorbed. All others pass through. The result is a mirror image of the emission spectrum. Bright lines become dark ones, each telling the story of electrons moving in reverse. Whether in emission or absorption, the pattern was the same, proving that Bohr's idea captured the very mechanism of atomic light. Behind the beauty of these spectra lay a new understanding of nature's precision. In the quantum world, nothing is approximate. Every photon carries an exact energy, every color an exact frequency. The universe is not a blur of continuous change, but a mosaic of discrete transitions. Bohr showed that the glow of a flame, or the radiance of a star, is built from countless identical events, electrons falling homeward, each releasing a perfect quantum of light. That regularity, repeated billions of times per second, creates the illusion of steady brightness. But beneath the glow lies an ocean of individual flashes, too rapid for human eyes to separate. Light itself became, in Bohr's hands, a story of structure, of disciplined chaos, of microscopic leaps producing macroscopic harmony. This explanation also changed chemistry. The way atoms bond depends on how their electrons are arranged, and those arrangements correspond to the quantized orbits Bohr described. The outermost electrons, sitting in the highest energy levels, determine how one atom interacts with another. When these electrons move between atoms, bonds form or break, releasing or absorbing energy, just like the photons emitted in spectra. Thus, the same principle that explains light also governs chemical reactions. The glow of burning hydrogen and the stability of water molecules share a single origin in Bohr's quantized orbits. Even beyond science, this discovery altered how people thought about the world. It revealed that light and matter are two sides of one process, energy transforming itself through jumps. Every flash, every reflection, every color in nature is the visible trace of electrons returning home. The red of sunset, the blue of the sky, the glimmer of gold, all owe their existence to these quantized transitions. Bohr's theory gave light a soul, connecting its beauty to a precise mathematical heartbeat. In simple words, he taught humanity that the universe does not glow randomly. Every beam of light is a message written in numbers, every spectrum a signature of identity. When we see light, we are witnessing electrons obeying Bohr's law, converting potential energy into photons of pure precision. That light travels across space, carrying the story of its origin, whether a laboratory flame or a distant star. When it reaches our eyes, it completes a journey that began with a single quantum jump. Bohr's explanation of hydrogen's spectral lines was not just a discovery of physics. It was a revelation about order itself. The smallest of atoms had spoken, and in its pattern of light, it revealed the hidden structure of creation. Bohr's atomic model was more than a clever diagram of circles and numbers. It was the spark that ignited a new era of science. Its impact rippled far beyond the hydrogen atom, transforming every corner of modern physics and chemistry. Before Bohr, scientists could describe motion, heat, and light, but they could not connect them at the atomic level. His theory built that bridge. It gave structure to the invisible and logic to the mysterious. It proved that the laws governing stars and laboratories, chemistry and electricity were all rooted in the same quantum foundation. With this discovery, the world stepped into the modern age of science. For the first time, the atom was no longer a philosophical idea but a quantifiable reality. Bohr's model became the cornerstone of atomic theory, explaining not only the spectral lines of hydrogen but the behavior of matter itself. It showed why atoms are stable, why elements differ, and why chemical reactions release or absorb light. It gave scientists a way to predict how atoms interact, how molecules form, and how energy moves through matter. What began as a solution to a simple question, why atoms don't collapse, became a key that unlocked the structure of the universe. The model's influence quickly spread into technology. Spectroscopy, based on Bohr's quantized energy levels, became the most precise analytical tool in science. It allowed chemists to identify elements by their light and astronomers to study the composition of distant stars. By observing the faint lines in the light from galaxies, scientists could measure their speed, temperature, and even their age. The entire science of astrophysics blossomed from Bohr's atomic insight. Each spectral line became a cosmic messenger, a whisper from atoms billions of light-years away, obeying the same laws as those in a laboratory flame. In the world of chemistry, Bohr's orbits gave meaning to the periodic table. The arrangement of elements was no longer arbitrary. It reflected the filling of electron shells. The outermost electrons, those in the highest orbits, determined an element's reactivity. This understanding explained why noble gases were stable, why sodium and chlorine combined so explosively, and why metals conducted electricity. Every chemical property could be traced to quantum structure. Bohr had turned chemistry into applied quantum physics. The impact on technology was profound. Once scientists understood that electrons could jump between levels and release photons, they began to harness that principle. The development of lasers, fluorescent lights, and LEDs all depended on Bohr's concept of quantized energy transitions. Even the functioning of transistors and semiconductors, the heart of every computer, rests on the same quantum behavior of electrons in allowed and forbidden states. Every display screen, every laser beam, every fiber optic signal carries the silent echo of Bohr's theory. He had not only explained nature, he had laid the foundation for the technological world, but the deeper significance of Bohr's work was philosophical. His model marked the end of classical certainty and the beginning of quantum realism. It taught scientists that nature's laws are not continuous or intuitive, but discrete and abstract. The universe does not allow every possibility, only those permitted by quantum numbers. It was a humbling realization. At the heart of matter lies not chaos, but a strange precision, an unseen order that human senses cannot directly perceive. This idea changed how science defines truth. To know something was no longer to see it, but to measure it, calculate it, and accept that the act of observation itself is part of reality. Bohr's model also reshaped education and culture. The simple image of the atom, a nucleus surrounded by orbits, became the symbol of science itself. It appeared in textbooks, company logos, and even the emblem of the atomic age. That image, though simplified, carried within it the story of human curiosity reaching the smallest scale of existence. It told people that knowledge could penetrate the unseen, that order could be found even in the mysterious. The atom became a metaphor for the unity of all things. The same patterns that govern stars govern the particles of our own bodies. Later advances, Schrödinger's wave mechanics, Heisenberg's uncertainty principle, and quantum field theory, refined Bohr's picture, but they did not erase it. His model remained the first clear bridge from the classical world to the quantum one, even when electrons were reimagined as probability clouds. Instead of orbiting particles, the fundamental truth of Bohr's idea survived. Energy is quantized and matter moves in discrete states. Every modern quantum equation still carries his fingerprints. Bohr's discovery also influenced how scientists think about limits. He showed that knowledge itself is quantized. We can know certain things with precision, but not everything at once. This humility toward nature became one of the defining philosophies of the 20th century. It encouraged physicists to look not for absolute truth but for consistent patterns, to accept paradox as part of progress. The acceptance of uncertainty, born from the quantum atom, became a new kind of wisdom, one that valued understanding over control. In the end, the impact of Bohr's atomic model reached beyond laboratories and equations. It changed how humanity sees existence. It revealed that the universe is built on invisible jumps of energy, on transitions too fast for the eye but too perfect to be random. It showed that the smallest event, an electron falling between two levels, can light up the cosmos. From that single idea came the science of the modern age, quantum mechanics, nuclear energy, electronics, and the exploration of the subatomic world. Bohr's model stands today as a monument to the power of imagination disciplined by reason. It began as a sketch of circles and ended as the foundation of quantum theory. It taught us that the universe, from atoms to galaxies, is bound by laws that are precise yet mysterious, mechanical yet poetic. Through his model, Bohr gave humanity not just knowledge, but a new way of thinking, one that sees beauty in structure, order in discontinuity, and unity in the smallest quantum of light. His impact was not only scientific but spiritual, reminding us that the fabric of reality, however strange, is perfectly woven. As the 20th century unfolded, Niels Bohr's legacy grew far beyond the laboratory. His atomic model had explained the hydrogen spectrum and given structure to the atom, but its deeper gift was philosophical. It changed how humans understand reality itself. Before Bohr, physics was a quest for certainty. for equations that would predict every motion of the universe like clockwork. After Bohr, science learned to live with mystery, to accept that nature reveals itself only in pieces, through patterns, probabilities, and paradoxes. His work became the foundation of quantum mechanics, inspiring a generation of thinkers who would reshape the modern world. The Bohr model opened the door to the study of quantum behavior, and once that door was opened, others stepped through. Schrödinger replaced Bohr's orbits with waves, Heisenberg replaced them with mathematical matrices, and Dirac unified them with relativity. Yet at the heart of every new theory, Bohr's central insight remained: energy is quantized, and the act of observation defines what can be known. His simple picture of electrons moving in fixed energy levels became the seed from which the forest of modern physics would grow. The equations of quantum mechanics still carry traces of his first postulates, and every modern discovery, from lasers to quantum computers, owes part of its ancestry to his model. Bohr's influence also shaped how scientists thought about the limits of knowledge. He believed that nature could not be described from one perspective alone. To him, light could be both a particle and a wave, matter both localized and spread out, and these dualities were not contradictions but complements. He called this principle complementarity, and it became one of the most profound ideas in science, that truth can have two faces, both valid, depending on how we look. This philosophy extended far beyond physics. It offered a new way to think about human understanding itself, that opposites are not enemies, but partners in revealing a larger whole. In Copenhagen, Bohr created more than a research center. He created a school of thought. His institute became a sanctuary for young scientists, searching for clarity in a world of equations and paradoxes. He welcomed them, not as students but as collaborators, encouraging open debate and creative freedom. Einstein, Heisenberg, Pauli, and many others came through his doors, drawn by the quiet authority of a man who spoke more in questions than in answers. Under his guidance, the foundations of quantum mechanics were laid. The discussions that took place there, sometimes lasting deep into the night, would define the intellectual climate of the century. Bohr's legacy also carried a moral weight. During World War II, as the implications of atomic science turned toward weapons, he became a voice of caution. He had helped reveal the secrets of the atom, but he never believed they should be used for destruction. He advocated for openness among nations, convinced that scientific knowledge should unite rather than divide humanity. Later, after the war, he spoke tirelessly about the need for global cooperation in nuclear research. To him, the atom was not a symbol of power but of unity, proof that all matter and all people share a common origin. The legacy of Bohr's model also extended into everyday life. Quantum theory became the foundation of modern technology. Electronics, semiconductors, magnetic resonance, solar cells, and even GPS satellites all rely on the quantum principles that trace back to his ideas. The world's economy, communication, and medicine are all shaped by inventions born from the atom Bohr imagined. His discovery was not just a scientific milestone. It became the architecture of civilization's progress, but beyond its practical fruits, Bohr's legacy lives in how we see the universe. He showed that nature is not a simple machine but a living pattern of probabilities, an interplay between what exists and what can be observed. He taught that uncertainty is not ignorance, but a feature of reality, that limits define structure, and that knowledge must always be accompanied by humility. In his quiet Danish voice, he had redefined the language of science. The universe, he said, is not about what we can control, but about what we can understand. That idea still echoes through every experiment in quantum physics. Today, when we picture the atom, we still see Bohr's vision, a nucleus surrounded by whirling paths, simple yet profound. It remains one of the most powerful symbols in human culture, representing both the precision of science and the mystery of creation. His model endures in classrooms, in art, in the logos of companies and research centers, as a reminder that from the smallest particles come the greatest insights. The atom is no longer a metaphor for division, but for connection. Every element, every molecule, every living cell made from the same quantum fabric. Bohr's legacy is not measured only in discoveries but in the mindset he left behind. He taught generations of thinkers to embrace contradiction, to see beyond appearances and to search for harmony between opposites. In a universe built from uncertainty, he found order. In a world ruled by paradox, he found peace. His model of the atom became a model for thought itself. Disciplined yet imaginative, logical yet open, precise yet poetic. In simple words, Niels Bohr changed how humanity looks at existence. He gave the atom a structure, light a meaning, and science a soul. From his ideas came not just equations, but an understanding that reality is deeper than the eye can see. A world built from quanta, where stability arises from leaps and light is born from the smallest transitions of energy. His legacy is the story of how curiosity became knowledge, how knowledge became wisdom, and how one man's insight revealed the invisible architecture of the universe. The Bohr model is no longer just a theory, it is the foundation of how we understand being itself, a reminder that even in the smallest atom, the universe is written in perfect, luminous order,